We build the future in rooms of light and factories of heat. Down quiet halls and behind heavy doors, a new world is being forged, piece by careful piece. These places, these factories of tomorrow, are not the loud, clanging workshops of old. They are more like laboratories filled with a focused calm and a sense of profound purpose. It is in these spaces that the minerals and raw materials of the planet we call home are transformed through incredible processes. What happens here matters now more than ever because the quiet work being done forms the very foundation of our modern lives, from the phones in our hands to the planes in the sky. It's a story of creation told not with a hammer and anvil but with beams of light and controlled fire. This journey takes us inside 4 remarkable scenes. Each one is a world unto itself, governed by its own rules of physics and precision. We will witness the delicate dance of robots in rooms cleaner than a surgeon's theater. We will feel the immense heat of liquid glass flowing like a captured river of lava. The scale of the work shifts from the impossibly small to the impressively large, from circuits measured in atoms to panels that will clad entire skyscrapers. Yet a common thread runs through them all: stronger, smaller, faster, more efficient. This is where human ingenuity meets the unblinking perfection of the machine. Each process we are about to see is a clear chain of cause and effect, a testament to science made real. A flash of ultraviolet light creates a pathway for information to travel. A bath of molten tin turns a glowing liquid into a perfectly flat, transparent sheet. Layers of fiber, when pressed and heated, gain a strength that defies their light weight. A pinpoint laser tracing a path through dust conjures a solid object from almost nothing. The beauty of it lies in this transformation, in watching a simple material become something extraordinary. The feeling in these places is almost cinematic, like stepping onto a film set designed to show us a glimpse of what is to come. Soft, ambient music might hum in the background, a steady rhythm for the smooth, deliberate motions unfolding before our eyes. The pacing is reflective, allowing us to absorb the details and appreciate the scale of the operation. This is not a frantic race, but a calm, steady march toward progress. We are invited to be quiet observers, to watch as the building blocks of our future are carefully, almost reverently, put into place. Now, let us walk into a semiconductor fabrication plant. This room is known as a clean room. The air itself feels different here, scrubbed clean of any dust or particles. Everything glows under a soft, yellow-blue light, a specific wavelength chosen to avoid damaging the light-sensitive materials. It is a quiet place. The gentle hum of air filters, the whisper-quiet movements of robotic arms. These arms glide along tracks with a dancer's grace, their purpose singular and precise. They are the silent workers in this sterile sanctuary, performing tasks with a perfection no human hand could match. The robots carry thin, shimmering discs of pure silicon, each one a perfectly shaped wafer reflecting the light like a dark mirror. These wafers are the canvas for modern electronics. One robotic arm gently places a wafer into a machine where it will be coated with a light-sensitive chemical. Another machine shines a powerful ultraviolet beam through a stencil or mask, etching complex patterns onto the wafer. These patterns are the circuits, tiny roadways and intersections that guide the flow of electricity, forming the thoughts of a computer. The scale is almost beyond comprehension. Millions of microscopic transistors, sometimes billions, built up layer by painstaking layer on a single wafer. Each acts as a tiny switch, a simple on or off that, when combined, performs the most complex calculations. A single speck of dust invisible to the human eye could land on a circuit and create a short, rendering an entire chip useless. This is why the rooms are so clean and why workers are covered head to toe in white suits, looking more like astronauts than factory employees. From these quiet, glowing rooms, the world is connected. After the wafers are etched, they are sliced into hundreds of individual chips. These tiny silicon brains are then sent out to become the core of essential devices. They power the smartphone that connects you to a loved one across the ocean. They guide the satellites that provide our weather forecasts and GPS navigation. They run the medical equipment that saves lives in hospitals. All of it begins here with a silent ballet of robots and light, turning simple sand into the engine of the information age. It's kind of miraculous, really. Let us move from the microscopic to the monumental. You step onto the floor of a large-scale architectural glassworks. You immediately feel a wave of intense, dry heat. The air shimmers. A furnace roars deep, the constant hum, with a white-hot chamber. Silica, sodium carbonate, and calcium carbonate are combined. A river of molten glass emerges from a channel, glowing orange-red like the sun. It moves like thick, incandescent honey, smooth, impossibly bright. Heat shimmers. You feel it on your skin from yards away. The molten glass pours in a continuous, wide ribbon. It spills onto a shallow, perfectly flat bath of molten tin. Because glass is lighter, it floats, spreading evenly like oil on water. The tin's flawless flatness imparts uniform thickness and a distortion-free surface. Workers in protective gear watch and guide the sheet with long tools. The ribbon glides into a long and closed cooling conveyor. Temperature is brought down gradually under tight control. If cooled too fast, stresses build and the glass shatters. Slow annealing locks molecules into a stable, transparent state. The orange glow fades to dull red, then to a faint cherry. Then it vanishes. Now solid, perfectly clear glass. At the end of the line, the cool sheet is a modern marvel. Automated cutters score the surface with diamond wheels. Massive panes are snapped off with clean, crisp breaks. Cranes with suction cup arms lift giant windows. Some panes are large enough to form an entire wall. This is the glass that becomes the skin of our cities. Transparent walls of skyscrapers. Crystal clear panels of breathtaking architectural designs. From simple grains of sand, cooked in a furnace, floated on liquid metal. We create the light and space we live and work in. Quite a powerful transformation. Section 4. The Patient Weave. Crafting the bones of flight. Next, we enter a new clean room. Just as clean and orderly as the previous, here again the air is cool and the dominant sound is the soft whirring of advanced robotics. We are in an aerospace composites manufacturing facility, where the super-strong, ultra-lightweight parts for modern aircraft and spacecraft are born. At the center of the room, a large, complex mold sits waiting, shaped like a section of an airplane's wing, a fuselage, or any number of components. Overhead, a machine known as a fiber placement robot moves with a slow, hypnotic rhythm. It is not spraying paint or welding metal. It is weaving. The robot's head precisely lays down thin ribbons of carbon fiber, each one pre-impregnated with a sticky resin. It follows a complex, computer-guided path, carefully placing one strip next to another, then another layer on top of that, oriented in a slightly different direction. It is like watching a giant, automated sewing machine, but one that is building up a solid structure from thousands of individual threads. Each layer adds strength in a specific direction, engineered to withstand the exact stresses the part will face during flight. This patient, layer-by-layer process is what gives composite materials their incredible advantage over traditional metals. Once the robot has finished its meticulous task, the part, still in its mold, is draped in a vacuum bag. All the air is sucked out, compressing the layers of carbon fiber tightly together. Then, the entire assembly is carefully rolled into a massive oven called an autoclave. An autoclave is more than just an oven, it is a high-pressure vessel. Inside, the part is subjected to immense heat and crushing pressure for several hours. This combination of heat and pressure cures the resin, fusing the thousands of individual fiber layers into a single, solid, unified piece of material that is stronger than steel, but weighs a fraction as much. When the cycle is complete and the part emerges from the autoclave, it is a finished piece of aerospace engineering. It is astonishingly light. You could lift a large panel that would have required a crane if it were made of aluminum. This weight savings is the key. Every single kilogram saved on an aircraft structure means it can fly farther, carry more passengers, or burn less fuel, making air travel more efficient and sustainable. These dark woven parts are the bones of modern flight, helping planes soar through the sky and rockets break free from Earth's gravity, all thanks to a process that turns simple thread into a material of incredible strength. Final stop, sculpting with lasers, growing the tools of tomorrow. Our final stop takes us to the cutting edge of manufacturing, a process that feels like it has been pulled directly from science fiction. We are watching advanced three-dimensional metal printing, also known as additive manufacturing. Inside a sealed chamber with a clear window, there is a flat, smooth bed of fine, gray metal powder. The space is quiet, filled with an inert gas to prevent the metal from catching fire. Suddenly, a brilliant, needle-thin beam of light, a high-powered laser, flashes to life. It moves with incredible speed and precision, directed by a computer that holds a digital blueprint of a complex part. The laser beam sweeps across the surface of the powder bed, tracing the first cross-section of the object. Where the intense light touches the powder, the tiny metal grains are instantly melted and fused together, forming a solid layer no thicker than a human hair. As soon as the laser finishes its path, a mechanical arm sweeps a fresh, thin layer of metal powder over the entire bed. The process then repeats. The laser flashes on again, tracing the next cross-section and fusing it to the layer below. Slowly, methodically, layer by infinitesimal layer, a solid metal object begins to grow, rising up from the bed of loose powder. This method of creation is revolutionary because it allows engineers to design parts that were once impossible to make. Traditional manufacturing often involves starting with a solid block of metal and cutting material away. Additive manufacturing does the opposite. It builds the part from the ground up, adding material only where it is needed. Incredibly intricate internal structures, hollowed-out forms, and complex geometries that are both strong and extremely lightweight. The process is slow and deliberate. The result is a single, unified piece with no welds, no seams, no weak points. Once the printing is complete, the build chamber cools. The bed is lowered, and the loose, unmelted powder is brushed or blown away, revealing the finished part nested within. It emerges like a treasure unearthed from sand, gleaming and perfectly formed. These parts are already changing the world. They are used to create lighter, more efficient jet engine components, reducing the weight of aircraft. In the medical field, they are used to print custom-fit implants, hip replacements, dental crowns, perfectly tailored to a patient's unique anatomy. This quiet dance of laser and powder is sculpting the very tools of our future, one layer at a time.